Welcome to your lesson on the nth term of a geometric sequence. So last lesson was arithmetic sequence. This time we're going to look at a geometric sequence. A very interesting real-life example of a geometric sequence is any kind of bouncing ball or object on planet Earth. The gravity causes the height of the bounces to follow a geometric sequence. All right, very big idea. Just as the last one was, these things are key ideas in further mathematics and calculus. Let's take some notes. You're going to use the same packet you used the other day for arithmetic sequences. So the packet began with a page that looks like this. Last time you filled in this side, which was on arithmetic sequence. Today we'll look at this side, which is geometric sequence. So here we are. Let's make the title Geometric Sequences. And these are defined as a sequence with a common, last time for arithmetic it was a common difference. For a geometric sequence, it has a common ratio. And ratio is just another way of saying a multiplier. So a common ratio between successive terms, and successive means one term after the next, right? So here is an example. It says find the next three terms in each sequence. First of all, looking at this, you can see it's 40, 20, 10. That number is basically being halved every time or divided by 2 every time. But usually when you think of a ratio, think of it rather than division, think of it as multiplication. So what are you multiplying 40 by to make 20? Well, you're multiplying it by 0.5 or a half. So 40 times a half, or half of 40, is 20. And then multiply that by half again to get 10, and on and on. So multiply 10 by half, or half of 10 is 5, and then half of that is 2.5, and half of that is 1.25. So that is we've just created a geometric sequence. And the R, we used D for common difference in arithmetic sequences, but here we use R to represent the ratio, or the multiplier. And in this case, the way to find the multiplier, well, we already know it's 0.5, but the way to find it is always to take one term and divide it by the previous term. So I took 20 divided by 40, and that gives us the 0.5, which is that multiplier. We could have used 10 over 20, we'd also get 0.5. We could have used 5 over 10, that would have also given us 0.5. So that's how you can always find the ratio. So in this one, it's a little bit harder, maybe tougher to spot what the multiplier is, or the ratio. But when you have a root of a number and then you have just a number, you may remember when you have roots, if you multiply by the root again by the same root, so if you multiplied root 6 by root 6, then the roots would disappear and you'd be left with 6. So the thing to multiply this by here is root 6. So let's confirm that from here to here we also multiply by the same thing. So 6 times root of 6 again, well, it gives us 6 root 6. That's great. All right, so next one is 36. Let's look at how that was created. Well, take this, multiply it by root 6, because that's our common ratio. So if you multiply this by root 6, this root 6 and the new root 6 would both cancel away the roots, and you'd have 6 times 6, 36. Then you have 6 times 6, which is 36. Now you take this one, multiply by root 6 again, and you get 36 root 6. So notice every alternating one has a root 6, and then the other alternating ones, the root 6 is gone because it's been multiplied away. So now when you multiply this by root 6 again, this root 6 and the new root 6 will cancel roots, and you'll be left with a 6. So 6 times 36 is 260. So the common ratio there, again, you can always find it by taking one term and dividing by the previous term. So I took 6 and divided by root 6. In this case, you look at that and you're like, well, that's not root 6. We just said the common multiplier is root 6 times root 6 times root 6. But in this case, we can, if you remember a rule about these things called radicals, we cannot have a root sign in the denominator. And to get rid of that, we multiply by root 6 over root 6. And that actually becomes root 6, because when you have root 6 over root 6, the bottom two root 6's turn into a 6, and that cancels away the top 6, and then you're just left with the root 6. That's a little tougher if you've never done radicals, work with radicals. Don't stress too much about that. All right, so how do we graph a geometric sequence? Here we have another geometric sequence. Here are the values, the terms in the sequence. Here are the positions. At position 1 we have 3, at position 2 we have 6, and so on and so on. Notice from 3 to 6 we multiply by 2, from 6 to 12 we multiply by 2, multiply by 2 again. So we're multiplying by 2 every time. That means that is 48, multiply by 2, 96, multiply by 2, 192. That means our common ratio is 2. That's our multiplier, times 2 every time. Let's graph it. 1, 3 is there, 2, 6 is about there, 3, 12, 4, 24. Notice something interesting happened here. With the arithmetic sequence, they were all lined up in a perfect line. They were linear. But with the geometric, notice it is starting slow and then rising very quickly. That's called exponential growth. So geometric sequences are always exponential. And we'll look more at exponential growth in the upcoming unit. All right, which are geometric from this list? We have these numbers here. Let's see if they're multiplied by the same number. Multiply by 3, multiply by 3, multiply by 3. Yep, we have a common ratio, which is r is 3, therefore geometric. Next one, is this geometric or not? Well, that's multiplied by 3.5. Then 7 to 12, you multiply by 1.7 to do that. So different multiplier already, therefore no common ratio, not geometric. Last one, how do you turn an 81 into a 27 and then a 27 into a 9? Well, you can divide by 3, but again, I want you to think of this always as multiplying. The ratio is a multiplier. So 81, if you're dividing by 3 to get there, then it's like multiplying by 1/3. So the multiplier is 1/3, and then 1/3 again, and then 1/3 again, and then 1/3 again to go from 3 to 1. So that's our multiplier. Common ratio, 1/3. Therefore, this is a geometric sequence. All right, how do you find the rule? We looked at how we created the rule for any term in a arithmetic sequence last time. Now let's look at how do you create a rule for any term in a geometric sequence. So again, here the multiplier is 0.5. You're multiplying by half, making it half its size every time. So r is 0.5. So let's think about u2. u2, this one, term number 2, is obtained by taking term number 1 and multiplying by the common ratio. And then term 3, you can take term 1, and to get from term 1 to term 3, you multiply by the common ratio once and multiply by the common ratio again. So you multiply by the ratio squared. That means r times r. You're multiplying by that ratio twice. So what do you think u4 is going to be? All right, try to write your own formula for u4 in the same kind of format. Hopefully you got this. All right, so u4, to get to the fourth one, you take the first one, u1, and you multiply by the common ratio 3 times, right? To go from the first one, you multiply once, twice, 3 times by the common ratio, so 3 times. And just like last time, there's a pattern here. The pattern is that this number is 1 less than this number always. So if you're looking for any term in the sequence, un, some mystery number term, any number can be in here, you take u1 and you multiply by the ratio, but you multiply it by the ratio n minus 1 times. So if this was 20, this would be 19 times. If this was 30, this would be 29. If this was 100, this would be 99 here, because you always have one less ratio multiplier to get to that term. All right, so that's our rule. So on your notes page, on the back where you have the 4 main squares for the 4 rules you're going to have to learn, or the 4 main formulas, put this one in for geometric sequence, nth term in a geometric sequence. There's the rule. And here's the example we're going to look at. So again, the multiplier here was 0.5, 0.5, 0.5. So using this rule, and we're looking for the 8th term, u8 is equal to 24, which is u1, times the ratio, which is 0.5, to the power n minus 1. And n minus 1 is 8 minus 1. So again, it's the first term times the ratio 7 times, because you'll have to do 7 jumps to get to the 8th term. So 7 jumps of 0.5. And that works out to 0.1875. All right, here's another example. This is now on the second page, which is stapled to your that first notes page. Look on, I think it's on the front page. Oh, no, probably on the back page. On the back page, it's all geometric sequences, and on there it says nth term formulas, and we have this example. Let's look at this one. The second term of a geometric sequence is -15, and the 5th term is 405. So again, this is similar to one we did for arithmetic sequences. We're actually given 2 statements there. We can make 2 separate equations. Let's start with the equation for the second term. So the second term, and using the rule, u2 is u1 times r to the 2 minus 1. All right, but we know the second term is -15. So I'm going to put -15 in here and replace this 2 minus 1 becomes a 1. So this is our first equation. Now let's make an equation for the second statement. The 5th term is 405. So u5, the 5th term is obtained by taking u1 times the ratio times to the power of 5 minus 1. And the fifth term it tells us is 405, so we put 405 here. 405 is obtained by doing u1 times the ratio to the fourth power, because we do the ratio of 4 jumps to get to that fifth term. So now we have this system of equations. This is different than most systems we see, which have plus and minus signs. We have multiplying here, but we can use substitution to solve it. I'm going to take this equation and solve for u1. So when I solve for u1, I divide by r on this side, so I have negative 15 over r. I got rid of the 1 there because it's just r. Now this u1, I'm going to substitute for this u1 here. All right. So 405 equals, and I've made the substitution, negative 15r here instead of u1 times r to the fourth. So now you have r fourth divided by r, because that can be written as r fourth here, and you're dividing. You have 4 r's on top, 1 on the bottom. You can actually cancel 1 r, and you're left with r cubed, because that r cancels one of these, and you have r cubed. Now you can solve for r, because it's an equation with one variable. So divide by negative 15, and you get r cubed equals negative 27. And then now you're thinking r cubed, so something cubed, something times itself 3 times makes 27. Well, 3 times 3 times 3 makes 27, but it's going to be a negative 3 because it has to turn negative. So r must be negative 3, because negative 3 times negative 3 is positive 9, times negative 3 again is negative 27. So that's our r value. Now that we have r, we can put that back in here and find what u1 is, the first term. So negative 15 over negative 3, and that gives us u1 is 5. So we were able to find the first term and the common ratio by creating two equations, making a system, solving it by substitution. All right, that's about as tough as these questions get. So if you understand that, good for you, good job. All right, there'll be more to try like that in the homework. So please do complete the homework assignment. It's linked on this same lesson. You'll see the assignment, and there'll be some questions to try. The questions begin with this one, so I'll actually have you begin your homework now. We're going to do number 1 and number 4 from the homework right now, so try it out. Read this question and try it out. Put your answer into Edpuzzle. Let's see how you do. So here's the answers. Hopefully you got that. Don't forget to get the ratio. You can always do one term divided by the previous term. So 8 divided by 4 gives you 2. That's our common ratio. So our multiplier is 2, and that makes sense. Multiply by 2 every time. And it says find the 20th one. So you use the formula and you get the 20th term. All right, the other question to try is this one, number 4 from your homework. Let's try it now. Please read it and give it a try. Check your work. The answer, R value should be 2. It begins by making one equation here and a second equation here. Solving that second equation to get R value right here. All right, and then the answer to part B is there as well. So hopefully you did all right. This one is a little bit tougher as well, but I hope you figured it out using just the one formula that we have. Please try the rest of the assignment. Practice hard. You can do it. Great job.